The second day of the second week of the BrainHack School. Today I'm going to present you some basics of fMRI signal and also a pipeline of preprocessing. So I'm going to make a basic introduction to fMRI. I guess some people here are already familiar with it. So I won't dig too deep into that very large topic, and otherwise I might hit some stuff I might not be able to fully explain. An MRI is an expensive machine that plays with hydrogen atoms, and which are widely present in our water-filled bodies. Like it's like the jokes we always say, like we are basically cucumber with emotions. So we have a lot of water in our body, and on water molecule you have two hydrogen atoms. So the hydrogen atom is just one nucleus with one electron, and so it's a very small magnet. If we place it in a magnetic field, its spins will align with the static magnetic field. And with coils, we can transiently modify that field and see how long it takes for this small magnet to align back with the static field. So when it returns to the steady state, it's going to send back some electromagnetic waves that we can measure with antennas. So, Another difference with animals is that we have blood. Another difference that animals have with cucumber is the blood. So the hemoglobin is also a small magnet, but its strength of the magnet depends on the oxygen attached to it. So the hemoglobin is carrying the oxygen in the blood, so it can carry or not oxygen. And so the oxyhemoglobin modifies locally the component of the relaxation that is called T2. So this local anomaly in T2 is called T2 star. And so when the brain is activated, it consumes more oxygen. So you would expect the oxygen to drop when there is activation, when in fact the brain activation triggers a massive response, notably by increasing the blood flow in capillaries. And so this response is slow and in a smaller time scale than the neuron firing, that is really fast. And we can see that we can see here a fit of this response by a combination of functions. That is a hemodynamic response function. So now we have a way to measure activity in the brain, but in fact, it's not that clean. The fMRI signal is quite ugly, so it's acquired at a lower resolution that we can have with anatomical image, because we want to acquire fast and to measure it continuously, to have multiple time points. So we acquire one volume after the other, and so there is a delay between each volume, which is called the time of repetition, or TR, and the slice of a volume are acquired separately. So here it's not fully separately, so I'm setting an example of a more recent acquisition where a number of slices are acquired in the meantime, so it's called multi-band sequence. So you have like all the blue slides acquired together, and after it's all the red slides, and after all the green slides. So this is a technique that appeared maybe 10 years ago and allowed to scan faster. And but also one other problem is that the Basile signal is not that strong. It explains approximately 2% of the total signal of the MRI, of the fMRI. And so here we can see a time series of like one voxel in fMRI, and we can see like it's not as smooth as the response function we saw in the previous slide. And a lot of it is not explained by brain activity. Also, there are multiple artifacts that spoil the fMRI and have often equal or larger variance than the Basile signal itself. Another problem is that the commonly used fMRI sequences are very sensitive to magnetic field inhomogeneity. So any hair tissue interface in the brain is gonna cause inhomogeneity in the magnetic field, and because the principle of acquisition assumes that you have a static field that is homogeneous, you're gonna have distortions, like we can see in the frontal lobe up there. So the brain is pushed back, and you have signal loss also. So that's another problem we have with fMRI. So that's why we need to apply a bunch of pre-processing steps to be able to analyze this data. And so pre-processing usually combines a bunch of steps in a specific order, and these steps can be classified in two categories. So the first category is registration, which deals with aligning stuff so that they can be spatially sound, such as correcting for motion, because the subject can move in the MR. Reverting the distortion we saw before, just to better align. We don't recover the lost signal, but we better align what has been distorted with a non-distorted image. And also aligning between modalities. So usually we have a T1 anatomical image, which is the high resolution image and almost undistorted one. And sometimes also we want to align with a template such as the MNI, this to allow group analysis. So registration method, to put it simply, just takes a model of deformation, so it can be linear or nonlinear, and a measure of how well it matches. So how one image matches the other, and so we're gonna distort one image and measure how much it matches the other, and we put that in an optimization algorithm. So on the other side, we have the denoising, which mainly works on the temporal dimension of the data. And so we're going to try to remove slow trends, for example, which are mainly due to the machine heating, and on motion and physiological noise. And this can be done, usually you have classes of technique for that, this kind of correction. So you have linear regression, or you can also decompose the signal with PCA or ICA and keep what doesn't look too much like an artifact. So I'm done with this introduction. I'm going to present a slide on FMRI prep, which is a BitZap pipeline that does FMRI preprocessing. Okay. So FMRI prep. It's not my slide, so I'm gonna present it. So it's a BitZap, and what it is, it's fMRI data preprocessing tool, and it's as I said, it's dealing with two main stuff like denoising and normalization. So normalization as registration and normalization to a group template, for example. And it's not an analysis toolbox. It's not doing GLM, it's not doing DCM, it's not doing connectivity, it's not dealing with dynamics of fMRI. So it's a first step in your processing of your data. And so the principle was to have a pipeline that is easy to install, that is robust, that works on any data. Like some steps, notably registration, can fail really bad, and sometimes you have brains that are not really well aligned, and so you want something that works like 99.9% of the case perfectly. And also it's what they call a transparent glass box rather than a black box. You want to have a view of all the steps and see why it fails and why some stuff are not as good as expected. So we're going to see at the end that they produce a report of all the processing steps. So it includes different steps, including T1 preprocessing, because when we do fMRI preprocessing, in fact, we always need a T1 because it's a better way to align to a group template, and we rarely process EPI alone. So the T1 and the EPI are going to be processed separately. And so the last one is transformation, so it's how you align two different atlases. So, yeah.
Say you scan multiple times the same person.
Yes.
Do you take the same T1 for that person?
Well, you have the choice. If you're interested into measuring changes in anatomical features, you would acquire multiple T1. But in general, for fMRI studies, you would acquire just one T1 and then align everything to that T1. So, like here, it's mainly for fMRI analysis. So it's not really the topic of VBM or cortical thickness is not really for that pipeline. But I guess we have a presentation tomorrow about anatomical image preprocessing. So, yeah. So so the T1 preprocessing is gonna deal with different stuff. We're gonna suppress some bias because the field and the gradient of the scanner are not perfectly homogeneous. So the intensity of the image varies depending on the location in the image. So we're gonna equalize that intensity across the image, and that helps the next step, which are the segmentation, for example. So the second one is skull stripping, and in skull stripping, you're just gonna extract the brain from the rest of the head because it's gonna help also the segmentation after. And so this uses ANTS, which is a toolbox mainly for anatomical image processing. So after that, you have a really basic segmentation that's going to like separate the brain into three classes, which are the white matter, the gray matter, and also the subcortical gray matter and the CSF. And then there is a next step that is FMRI co-registration, which uses ANTS again. For the EPI preprocessing, the usual first step is to correct for motion. So everything like the voxel is going to represent the same area of the brain. That's really important to do that first. You have again a skull stripping that is based on nylon, and co-registration with a T1. This one uses a specific cost function, so it uses the interface between gray matter and white matter, and it tries to align the EPI so like the gradient of intensity across this boundary is maximal. So it's a more recent registration technique, and it works quite well. And during the EPI preprocessing, also you're going to estimate a number of confounds that you're not necessarily correct the image with, but you have it for your analysis, because regressing confounds is really dependent on what you want to do as analysis. Sometimes you want to remove it, or you don't want to remove it. So most pipeline now will output the image and a number of variables that you can regress out of your data or not, or like take into account into your statistical analysis in a way or one or the other. So it's gonna extract like the frame-wise displacement, for example, that is the amount of motion between two TRs. The global signal, that is the average, like an average of all the time series in the brain. And sometimes it's really artifacted by motion. And physiological noise, and also like an average in different tissue. Like for example, we can extract the average in the white matter because we know there's not much activity there, and in the CSF also. And the last one is COMCORE. It's a bit like the same thing as the global signal or the mean tissue signal. It's just that it's going to take PCA instead of an average. So you take a number of component of the PCA to describe the base signal variation in different regions. And so the last one is EPI transformation. So when you want to bring an EPI to a template like the MNI, you just like in the past you didn't care much if you apply multiple steps of interpolation. So it's going to smooth the data a lot. When you do SPM, for example, a statistical map, it's good to smooth because it's going to increase the signal-to-noise ratio. But today we want to do machine learning, so we want to keep the fine patterns of activity. So most of the pipelines today is going to try to interpolate all the steps interpolate all the transformation in one step. So you have the motion correction, you have the transformation from the API to the T1, then from the T1 to the MNI affine, and to the MNI using nonlinear registration. And so all these steps are going to be interpolated once, so you keep the finer details of your API image into the MNI template. And well, the node sampling fact, the point is just like you keep the original voxel size. It's usually save space on your disk. And so the inputs is a bits formatted data set. I guess you've been presented with bits and what it is. And the outputs you're gonna have for the T1, the image corrected on which the intensity has been corrected with N4. You have the brain mask, you have the different tissue that has been segmented, and you have a registration to the MNI. And you can also bring image from the MNI template to your individual space if you want to perform your analysis there. Sometimes it's good to do analysis in the individual space, in part to avoid the interpolation and reduce the blurring of your image. And for the API, we're going to have the motion-corrected image, the brain mask, the affine registration to the T1, and also like the noise confound that we discussed earlier. So you have all volume in MNI and native API space. So you can choose in which space you want to do your analysis. And so this is a structure of the image of the files that get extracted from that. Okay. So it follows the bits convention, even if it's not included in the bits convention. So it's structured the same with the subject, the session, and the anatomical and functional directory. And the last thing is that it produces reports. And so for I'm going to present the report just after. For the installation, it's easy to install with Docker on your own laptop or desktop. And it's easy to install also with Singularity to run on HPC because when you want to process a lot of subject, it's quite heavy. Something that is not presented in this presentation is that now FMRI Perp include FreeSurfer, so it's really a long preprocessing to extract the cortical surfaces of the brain, and so running it on an HPC makes really sense with that. So as it's a container, it contains all the dependencies, so it's really easy to install. So I'm not going to go through the detail of that. Kind of specific to their infrastructure. And so you have a number of options. It's a pipeline that by default is going to choose a number of default options, but you can set up a number of options to either limit the memory or skip some steps. Like for example, FreeSurfer, if you don't care about the cortical surface, you can skip FreeSurfer and run your analysis, your preprocessing faster. So I encourage you to look at the documentation and choose what options are the best for your project. Okay, and I'm gonna skip to the presentation of a report. So when you run FMRI Perp, it's going to produce an HTML report that you can just open in your browser. So it's really easy to look at what happened in the pipeline and if it went well. So you have the different steps. For example, the skull stripping, so the removal of the skull. So you have the red lines here is illustrating the brain mask, and also the segmentation of the different tissue in the brain. You have the normalization to T1 reference. So if you overlap here, so it's going to alternate between the participant and the MNI template. So you see that it's when it switches, it's barely noticeable. So I think the alignment works well. you have also, you can specify multiple templates. So like I think this one is another variation of the MNI template, and so you can output your data in multiple space if you want. Here we can see the surface reconstruction with free surfer. So you have again the interface between white matter and gray matter and the CSF outside. Fast. So for the functional, we have all it's a really verbose output. So you have the result of the distortion correction. It's something that wasn't in the slides, but so we can correct the distortion. So it's going to alternate between the two, and you see that some parts are recovered here. You don't really recover the signal, but it's better aligned with the brain. So it's with the brain in the T1 anatomical image. It's not perfect, so depending on the type of acquisition you have, it's going to apply a different type of correction for the distortion. So it's not always as good depending on the data set you're going to be using. Yep.
Question regarding the schedule and
Yeah.
distortion correction. What acquisition does it mean?
So in the past, like most people, yeah.
Can you just repeat the question for the video?
Okay. The question is what kind of acquisition you need to perform the susceptibility distortion correction. And so in the past, most people would acquire field maps. So it's a type of acquisition when you're going to measure the phase of the image, and you have when you acquire two different echo time. So it's the time between the time you excite and the time you read the measures from your MR, and so with these two echo, you're able to estimate the field inhomogeneity itself. Like you're able to have a measure. An absolute measure of the field inhomogeneity. The problem is that it's not easy to apply. You have to run a lot of steps, and sometimes it doesn't work that well. And many people acquired it in the past, but never applied it because like there weren't any pipelines that were robust enough to apply it. Nowadays, I think most people use what is called phase inverted acquisition. So you're going to acquire one. You're going to acquire your usual fMRI study, and you're going to acquire just like a few volumes with a phase reverted. The phase encoding direction is inverted, and so the distortion is going to be the other way. And so with an algorithm that try to find the distortion by like stretching things, and you're going to be able to find like the undistorted image. So you to align the two images, like the one with the one phase and the other phase, you have to push in the same direction for the two images. So most people use that. I think there are also some spiral echo imaging, but it's not really often used for fMRI. That measures the field inhomogeneity during the fMRI acquisition, for example. So yeah. Does that answer the question? Yeah. So depending on the data set, you're gonna have the different cases, maybe the field map or the phase inverted acquisition. But the bit standard is specifying that. So usually, like the pipeline, like fMRI prep, is able to detect what kind of field map is given, and gonna do the right preprocessing for that. So the next step is the alignment of functional and anatomical image. So for this step, they put the boundaries of gray matter and white matter and CSF, and you're able to see how well it aligns with the T1, and it switches between the T1 and the EPI. Next, you have some mask. Like usually for CompCore, you're gonna take mask in the template space, for example EMNI, and you're going to bring it into the EPI space. This mask mainly represents the deep white matter, and you're going to measure signal in there because you know it's where you're going to find noise and not brain activity. So you can take that signal as as a noise signal to regress out from your gray matter voxels. And you have different graphs for that the PCA on these regions, and in the end you have this graph here. You have so the global signal in red, the global signal in the CSF, the global signal in the white matter. You have divars, I don't remember exactly what's that. And the frame-wise displacement, which represent the motion. So you can see here that the subject moved a lot at that point. And here it's what is called a carpet plot. So it's showing all the voxels here and the time in the other direction. And so you're able to see if there are any major artifacts. So you can see here that because of the subject motion, you have a huge change in signal in like almost all the voxels of the brain. The voxels are categorized in the gray matter, the subcortical gray matter, the white matter, and the CSF, I think. And so you can see that when the subject moves, you have a huge impact. And in fact, in this carpet plot, you rarely see the effect of the task. So like the real ball signal, you don't see, like, for example, a block where the subject moves his hand or something like that. So it's you usually only see artifacts in there. Yeah. So it's also like showing you the correlation between the different count founds that it extracted from the pipeline, and so sometimes you want to see if they are correlated. If you want to regress them out, if they are correlated, it's going to be a problem because they are not orthogonal. So it's going to make your general linear model not well specified. And so one step that wasn't described in the slide is the ICA decomposition. So they have an ICA-based noise correction, so it's going to apply ICA to your data and classify the different components into good or bad. So we can see here the red traces are bad components that you want to eliminate. So the ICA you're going to decompose, and after you're going to only take the components that are good and recompose the signal with that. And we can see that this kind of temporal signal doesn't make really sense. And here you have the power spectrum of that signal, so it's a really fast signal here. And we can see that even the spatial pattern of this artifact is not really functionally relevant. Same here. You can imagine that it's because of the huge motion of the participant that this changed a lot, especially because he moved, and so the part that wasn't in the field of view is now there, or the contrary. And you have other components that are making sense functionally. So, for example, here you see a huge activation in the visual cortex, and you can see that here you have some stuff that resembles certainly the blocks of the task for that data set. And so you have maybe something like 40 components. And so here, for example, you have maybe response with like it's activating some region in just a number of the blocks. So you have another pattern of activation. Here it could be, and this one it could be maybe the motor response of the participant, like maybe he used his right hand, and so the left motor cortex is activated here. And I think that's it. And what it does also, it produces an HTML, a method section for your paper, so you don't even have to write the method section for the pre-processing, which is really good. So you just can take the markdown, the LaTeX code to put directly into your paper, and you don't have to explain anything about this. So you don't even need to be an expert to write your paper on FMRI. And it's really long. Like, you have a lot of sections. They give you all the reference for all the tools that are used in your pipeline. And I guess that depending on the steps in your pipeline that you activated or not, it's going to change the method section accordingly. And yeah, so that's it. Do you have any question? At least you don't have a blank page when you start writing a paper. You already have like the beginning of your method section. It's good.
Maybe do you want to touch a word or two on like how you go to configure that and run that?
Yeah, I think for like configuration for installation, I guess the easier is to use Singularity or Docker. I would say Singularity because I encourage you to use Compute Canada resources. So just I guess you just have to do a Singularity pull with like a kind of URL for that pipeline in particular, and so it's gonna give you a CMG file. And after you can just run your pipeline with that Singularity. You bind your data to attach your different data set to the Singularity container itself. So the name of the container, and after all the options for FMRI prep. So I think maybe we can find it here. Just wondering if there was some. Yeah. So the main option are the main arguments you have to give to FMRI prep are the data set that you want to input, where you want your output of the pipeline, and usually you say that you want to work at the participant level. It's a standard for BitZap, but in fact FMRI prep only works at the participant level. It's a standard way of putting the argument for BitZap. So this is not relevant, but you have to put it anyway. And you can specify a directory where you want like temporary files to be put, like because you have a lot of intermediate steps in the pipeline. So you can set, for example, a hard drive that is faster to put the temporary output of the pipeline. Yeah. Any question? Yeah.
This is unrelated to what you just went through, but if I have structural MRI data, can I do some things on MRI prep?
That's a good question. I guess maybe if you input a bit data set with only anatomical, maybe it's gonna do the anatomical step, but won't do anything for functional. But
So
I would.
SMRI prep.
There is SMRI prep.
Yeah.
Okay.
I don't know to what degree of readiness it is though.
Yeah.
And there's a NANS BitZap as well.
Okay. Yeah.
NANS is like one of the standards.
Yeah.
to
But
actually
depend-
what's used by.
But I'm sure there are like BitZap specifically dedicated for anatomical preprocessing, depending on if you want to do a cortical thickness or VBM or anything like that. So I guess there are some BitZap more appropriated for that. But if you have a data set where you plan to do some cortical thickness but also functional MRI, like running FMRI prep will allow you to do both. Like the output of free software will be there, the output of the ENS registration to the MNI will be there, so you can do VBM also. Yeah. A quick poll: who think is going to pre-process FMRI data during their project? Raise your hand. Okay. So do not hesitate to come and ask me questions if you want to.
Yeah, I think it'd be great to organize some like a little clinic for you to get that going, because nobody says you just download the image and just do it. But
Yeah.
there's some like details.
Yeah. But before like running 500 subjects, maybe like just look at all the options and see what's really necessary for you, because it can take a long time. And
also when you want to distribute your computation on a high performance computer, you need to use their scheduling tools, which are not integrated in FMRI prep. So there's a few scripts to write in order to actually distribute your 500 subjects, potentially on 500 different CPUs.
Yeah, usually, you're right. Yeah, usually you're gonna like send like 500 different Singularity run with one participant in each. So it's gonna be a better way to
Basile
distribute.
can help you with
Yeah.
that.
Yeah. Any question? Okay.
Okay, so I guess we're back to the